Okay, good morning all of you. Yesterday I have uploaded a few things. I have uploaded the PPT regarding two-way slabs, flat slabs, staircase, columns and all those things. And then I also uploaded some for the things which I have given an assignment on, basically flat slab, staircase, and then what is the slender columns, and then footings. So for these 4 topics I have uploaded some PDFs, basically scans of one of the books that I usually use for teaching in the class. So based on that, you can read them and you can start working on your assignment. You can work it as a group, but when you submit it individually. Okay. The last of those assignment problems, which is footings, I am going to start today. So the remaining things we can actually start working on. Okay, for footings, I do not have a PPT with me, so I'm going to take it in the traditional way by just writing everything on a board. In this case, our whiteboard. So this is the last part of your syllabus, which is footings. It will be covered probably in a bit of. Okay, so we're going to look at footings now. Okay, so where is the footing located usually? Where is the footing located?
At the bottom of the column.
The bottom of the column. And when you talk in terms of levels, like your
level.
Plinth level and those things, where is it located with regard to plinth level?
Below the plinth level.
Below the plinth.
Yeah, it's below the plinth level. Okay, so below the plinth level you may have a continuation of the column, and then below it you may have your footing starting. Okay, so you would have done geotechnical engineering till now. So what are the 2 types of foundations that you have learned in geotechnical engineering?
So deep and shallow.
Deep and shallow. So what in general footings come under what type of foundation, shallow or deep?
Mostly shallow foundations.
Usually these will belong to shallow foundations. In fact, I can say it's always shallow foundation. If it becomes a deep foundation, it becomes a pile. If it's a pile, we don't technically call that as a footing. We call it just as a pile. Okay. So this is where your footings come, and these shallow foundations usually they will be made of our reinforced concrete. Okay, very rarely they use other materials than reinforced concrete. If it's a deep foundation like a pile, then it may be steel or concrete encasement, or rarely timber. Okay. So this is what a footing basically is. So if you have your plinth level, okay, this may be ground level. Plinth level may be a bit raised. It depends. Okay. Okay, you may have a backfill or whatever. So you may consider this as your plinth level. Okay, so if there is a column, so you may have a continuation of the column below the ground. Okay, and then you may have your footing coming. Okay, so basically it's only this part which is known as a footing. Okay, only this is your footing. Your column, in fact, whatever is in this part and all is still your column. This part does not form your footing. It's only this part that actually widens out and comes. That only is known as your footing. But in any case, this whole thing is known as substructure. Okay, everything which is above this is known as a superstructure. So these are all basic civil engineering terms. So the main thing that decides the design of your footings is, one thing is basically this thing is resting on some sort of soil. Okay. And you may know from your technical investigations, you have studied a lot of types of soil investigations. Okay, can you name a few types of soil investigations that you have heard of? Some tests.
SPT.
SPT. So why is that SPT quite important? What is the form of this? What is the full form of SPT?
Standard penetration test.
Standard penetration. So what is the use of this test? Why is it important?
Find the parameters like the angle of friction and cohesion.
Find the parameters like what?
Like angle of friction and cohesion, and from that we can find the bearing capacity of the cell.
Okay. So basically you find a few things. One is your angle of friction. Okay. Then so this gives you from your standard penetration test. There are other things also which come. One is you have a number known as N. Do you know what this N is?
Number of blows required.
So basically the number of blows has a direct relation to the actually the firmness or the bearing capacity of a particular soil. Okay. So maybe if you get these two parameters, and there are ways by which using this N, angle of friction and those things, you will be able to arrive. I'm not sure. Maybe you might have studied the calculation, but I'm not sure exactly if you have. You will be able to calculate something known as SBC, or safe bearing capacity. Okay. Are you doing geotechnical 2 now? Or geotechnical 1?
Geotechnical tools.
Okay, so these things did you learn in GT1 or GT2?
In second one.
Second one. Okay. So basically, you have this. You will do a certain soil investigation like SPT. Basically, where so if it is a normal depth of foundation, you can directly use an SPT. Otherwise, no. If you have to go deeper, then you will have samplers. Okay. There are different types of samplers which, when bored or drilled below, you'll be able to get a sample of the soil. It's a disturbed sample. There are two different types of samples in soil: disturbed and undisturbed. You will get a disturbed sample, but anyway, still you'll be able to evaluate some parameters approximately to find your SBC. Okay, so this footing, design of the footing depends a lot on your SBC, as much as it depends on your grade of concrete and your grade of steel. Okay, grade of steel is, it probably plays the least role in design of footing. Okay, the biggest role in the design of your footings is your SBC and your grade of concrete. Okay, so now coming to this SPC. So basically, this SPC tells you how much pressure can be allowed to be given to the soil by this footing. Okay, how much pressure can this footing give to the soil? Okay, so if the pressure coming from the footing exceeds the SPC of the soil, you may have some problems, such as, can you guess a few problems based on your geotechnical knowledge? If the load or if the pressure coming on the soil is more than what it can stand, what do you think will happen to the object that stands on the soil?
Settlement.
You'll have settlement. Okay, sometimes this settlement is differential. So there's something known as differential settlement, meaning that one part of the structure may settle more, other part of the structure may settle a little less, and this may cause a lot of problems in building. Like, you'll have a lot of cracking. Okay, you'll have crack on the walls itself. Okay, because of so when you have something like this, say this side is settling. Okay, so if this side settles, say this is the type of settlement that is happening in your structure. Okay, so basically, this will be the soil will try to push this up, and this will try to be taken down a bit. Okay, so under this action of forces, one is up and one is down. What occurs in this? What occurs in this plane because of this set of forces? So you have opposing displacements. Okay, one is going down, others tending to stay up because there is no settlement on one side. So what kind of a force is set up in this plane?
Torque.
Torque, but it converts itself into a shear. Okay, So you will start having shear cracks. I will call it as, you'll start having diagonal cracks in your walls. Whenever you see a crack like this, it means somewhere there is differential settlement happening. Okay, and because of this, of course, your beams, columns also may start having cracks. Okay, you start having cracks in your. So anyway, this is known as differential settlement. It happens if your SBC is not so good. Okay. Okay. So now coming to this SBC. So in general, typically we'll have ranges like something between 150 to say about 300 at most in many cases kilopascals. Okay, 150 to 300 kilopascals. This is the normal range of SBC, in which you can very comfortably use normal types of footings. Okay, so this is for soil. Some cases, if you have greater than 300 kPa, okay, this most likely implies that what you are resting your footing on, it may not be exactly soil, it may be something else. Okay, the footing may be, if you calculate your SBC to be more than 300 or 400, okay, it's not a fixed number, but if it's usually greater than probably 350, let me say 350 is a better number to use. So it's more than 350 kilopascals. It mostly implies that you are resting on firm strata or rock. Okay. In the other end of the spectrum, if it is lesser than about say 100 kilopascals, okay, then it might not be suitable for normal footings. You may have to go for rafts, okay, or if you want to find, see for example, this is the soil. So this is a certain depth of soil, say H. Will the SBC be same everywhere along the depth? Does the bearing capacity of the soil remain same all these places, all these layers? Or are they different? Are all these equal or different?
So they depend on the depth.
Okay, so where do you think they'll be better and where do you think they'll be smaller?
More the depth, more the bearing capacity.
So usually when you keep going down, your this thing will be more. Okay, your SPC will be more as you keep going down. Except if you go so much down that you hit the water table, then you'll have no saturation and all, and you'll not have good SPC. But otherwise, so as you go down, you'll have to better depths. You may have a better SPC. So whenever, usually our foundations may be at say some depth like this. Okay. So if this SPC is not sufficient, like it's 100 kilopascals or something, then somebody may choose to give a pile. Okay, so that they end up at a place where where we have a bit of firmness. Otherwise, they will use something known as a raft. Okay, have you heard of this term known as a raft or a mat foundation? Have you heard of rafts or mat foundations? Have you heard of this?
Yes, sir.
Okay. So basically, it's something which is, it's not a single foundation. It is something which covers the whole area. Okay, it's like a huge slab. Okay, it's like a very huge slab which rests on the ground, and on top of that slab you will raise your columns and other things. Okay, that's what it to be very simply, that's what a raft is. Okay, now look at these values: 150, 350 kilopascals. Okay, this is about 350 kilopascals. So everything I have used kilopascals. Okay, how does it compare with the grade of the strengths of your concrete and steel? Which is more? Is this more or is this more? What is the unit I write for, say, for example, if I say M20 or M25, or if I say FE500, that 20 and 415, what is the unit?
Megapascal.
Megapascals. So which is more, this or this? Soil or concrete? Which has more strength?
Concrete.
Concrete. So what is the order of difference? Approximately.
10 power 3 times.
Yeah, 10 power
3.
10 power 3. So the order of difference between the strength of a concrete and the safe bearing capacity of soil is, it's about, soil is about 10 power minus 3 in order as compared to your steel or concrete. So therefore, the basis of doing a foundation design is, I have a column, okay, I have a certain load, and say that I have designed this column perfectly for, say, M20 concrete or whatever it is. So it's M20 concrete, it can only, concrete can take only, if this is M20 concrete, the stress in this concrete can only be 20 megapascals, it cannot be more than that. Okay. So if you include factor of safety and all, it cannot be even 20, it will be lesser than 20. Okay. But anyway, let us say for the sake of it, that this pressure is M20 or 20 megapascals. So when you come to this footing, if I do something like this, okay, I just take the column and I rest it on the soil. Okay. If I do this, what happens is this soil will have to take 20 megapascals. Okay. This cannot be, and the safe bearing capacity of soil is some maybe 100 or 200 kilopascals. Okay, which is far away from 20 megapascals. Okay, so I have this much stress on the column. I cannot change the load which comes. Okay, the load which is coming is fixed for the building depending on its usage. I cannot say that let me reduce the load coming on this column. That is not an option. Okay, that load will come anyway. So if I want to, if this load whatever is coming, I want to reduce this load to something in the range of, say, 200 kilopascals. What can I do to reduce the pressure on the soil to this much value? So if you have, yeah,
increase the area.
you can increase the area. So that is the reason why all your footings are actually made like this. Okay, this is basically done so that your area increases a lot. Okay, such that you can bring the pressure on the soil to within the range of its soil bearing capacity, of its safe bearing capacity. Okay, so this is the principle behind doing any foundation design. Okay, now let's look at the different types of foundations. Okay, so this is a recap of something you might have already learned in geotech. Types of footings rather, not foundations. We are restricting ourselves only to footings, not to piles or any other thing. Okay, so if I have a footing, this is a column, and I'm putting the footing like this. What is the name of this type of a footing? Probably if I write in plan, it will look like this. So this is the footing, and this is the column. Okay. What is the name of such a type of footing? You have a column and you have a footing below it. What is this type of footing called?
Rectangle.
Huh?
Rectangular.
Okay, shape is rectangular, but any other
Isolated footing.
isolated footing. Isolated and rectangular. Of course, if you have a circular column, you can obviously also make it a circular isolated footing also. That is also allowed. Okay. So, though in many cases, even if it is a circular column, many times people will tend to use still a rectangular footing. But anyway, you can, if you want, you can use a rectangular footing. Now the same thing, same isolated footing. Many times I may not want to give it like a sudden rectangle. Rather, I want to give it like this. Okay. So this is also isolated, but it is a different type. It's isolated and sloped. Okay. Now the follow-up question is, what is the advantage of giving a shape like this as compared to a shape like this? In what ways might this be better as compared to this?
Here the pressure reduces gradually
Pressure reduces where?
in case of sloped footing.
Yeah, pressure on which point? On which part?
On the bottom and the footing place.
No, see, if I on the footing, the pressure will be same if as long as this area is same as this area, no, then the pressure on the soil will be more or less it will be the same. So that is not exactly the advantage. Any other cases?
So the lateral pressure will be less.
Lateral, you mean like coming from this side?
Ah, yes, sir.
That will be actually you have maybe okay, maybe marginally that may occur. Fine, okay. There may be you may have slight advantages in the lateral pressure, but that's not the major thing because the lateral pressure is almost very less. It's not much compared to the pressure from this. Okay, because usually this isolated, these footings and all usually will give for a very normal depth, like like maybe maximum of 2.5 meters usually. Okay, so for 2.5 meters and all, the lateral pressure which acts, it will be there, but it's not the main problem. But maybe okay, fine, maybe lower lateral pressure. I won't say lower. Yeah, I can rather say better lateral pressure resistance. But this is not the biggest advantage, so therefore I put a question mark. Rather, what is the main advantage of this? Okay, I'll do one thing. I'll reverse this shape. I'll draw the shape upside down. Okay. Okay. Can you make any guesses what may be the advantage of giving the shape then?
Maybe the load may be distributed properly, sir, because in that column the load may not be distributed completely throughout the places, sir, but in this the load may be distributed throughout exactly with proper, sir.
Okay, so you're saying that load will get distributed properly, it will slowly come into this part.
So like it properly gets distributed, but in that case it may not be full load cannot be distributed exactly, sir.
Better distribution.
So better shear resistance.
Okay, good. This is a better, yeah, this is a better answer. Better shear resistance, but still you're coming to it, but you're still not got the main. Better shear resistance. This is a definite advantage because you have greater depths. Okay, at this point. But anyway, for this question also I can tell you. Okay, I want good shear resistance. So why not instead of keeping it like this, I might as well make a bit thicker footing now. to have the same shear resistance as this.
So the material used is less over here.
Okay.
Than that.
For the same material, to achieve the same shear resistance, you are sloping it. Okay, fine. Good. Fine. Shear is better. Shear resistance is better than. What is the other thing other than shear? What is the counterpart of shear?
Punching shear.
Punching shear also no. You need both shear. One way or punching. This applies to both. Okay. What is the other thing that you always deal with other than shear? What does this look like? Okay, I'll break it down further. If I look only at this part, what does this look like?
Cantilever.
Okay, now in a cantilever, so you look at this as two cantilevers hanging from two sides. So what will be there? What will be there here and what will be there here?
Bending moment.
You will have a certain bending moment. Okay, so basically this pressure which comes from, so there's a load applied from the column and it will be transferred to the soil. So this soil, what it does is it will try to resist it. It basically resists the load which is coming or the pressure which is coming from the column. So the pressure from the soil will always act upward on the footing. Okay, this always acts upward on the footing, and therefore you will have some moment on the base of the footing. Okay, so if you have on an isolated footing, you will always have a moment distribution like this. Okay, you will always tend to have a moment distribution like this, and you say that no, because here there is zero moment, I do not want the greatest thickness here. I just want a nominally sufficient thickness at this point, but the thickness for the moment what I need, I want it to be present at probably at this location. Okay, so therefore instead of using the same thickness throughout, you accordingly just vary the thickness in accordance to with the bending moment. Okay, so this is the reason why sometimes there is, so it confirms or it is according to bending moment on the footing. Okay, so this is why many times people use this kind of slope footings. It is for these particular reasons. And then the next thing is I go to another type of footing which is like this. I have two footings or more than two. Okay, two or more than two, and I give something like this. What type of a footing is this called?
It's a combined footing.
It's a combined footing. Okay, so as long as this P and P are more or less the same. Okay, P1, P2, if P1 is approximately or more or less same as P2, you can just give the same type of combined footing. You may have a case where sometimes you have something like this P1, P2, where your P1 is reasonably greater than P2. Then you may want more area near P1, so therefore you probably would choose to give the footing like this. This is also combined footing, except you are compensating for the area because there's a larger load on P1. Okay, so this is combined footing. So these two are the main types of footings that you're going to study in this course: isolated footing and combined footing. Isolated footing, you will be seeing a few problems. One problem. I won't have time for more than one. So one isolated footing problem I will teach for you. Combined footing forms a part of your assignment. Okay. So this is the thing. And the other thing that we have to note a few points about this footings is, so when you do your soil pressure calculation, okay, when you calculate your soil pressure, you will compare it with SPC. So when actually doing this soil pressure calculation, there is one important point you should remember is this soil pressure calculation should be based on service loads, not on ultimate loads. Okay, now what is the differences? If you remember, for doing a design of beam, slab, column, whatever it is, what was the factor that you used to multiply dead load and live load?
1.5.
You use 1.5. Basically, that is an ultimate load factor. But when calculating a soil pressure, okay, so what I mean is, so you may say that you have some dead load plus some live load, okay, and this is, and then you say that this just go a bit down. So you may say that this is some B by L area of footing, okay. So you may say that you're finding the pressure on the soil as your DL plus LL times B by L, okay. So one thing you should remember is when you, so it's, let me say not say DL plus LL, I'll just say P. Because it will confuse a bit if I show dead load and live load acting on a column. Okay, it doesn't directly act on the column, it acts on the beams and slabs. Okay, so you would have done an analysis, you would have used factored loads 1.5 times dead load plus 1.5 times live load. You would have applied it on the beams or on the slabs. Then based on what you applied, you would get some reaction on the beams. That reaction on the beams comes to the column as P. So basically this would have been based on 1.5 LL plus DL. Okay. But when you try to calculate this soil pressure calculation, you have to make sure that the loads which you have used for this P, it should be based on service load factor, which is usually 1.0 not 1.5. Okay, so this is one thing to remember. So when you, so somebody, if they give you, say that a factored compression of this much comes on a footing, so you should know that, okay, this is factored, let me divide it by 1.5 before you calculate the upper pressure on the soil. Okay, so this is something that you should always remember. Okay, so this is one point. So this is as long as you have just pure axial compression. Okay. So another thing is usually above this footing, you have some soil. Okay, so you have some soil acting on this. Okay, say some depth of soil. So this depth of soil is not included in P. Okay, and before you decide the size of your footing, you may not know what is this. You may not know what is the total weight of soil acting on this footing. So this much soil, this soil weight also acts on the footing. So that is not known prior. So one good usually used correction for that is you'll do into 1.1. This 1.1 is basically to take care of any soil that would have been present on top of the footing. Okay, this is just an approximation. So that is again something. This is known as, it's known as a backfill. Okay, so the weight of the backfill also sometimes needs to be considered. Okay. Then finally speaking, we have our so if we have some footing, okay, and if I have P and moment, okay. So in this case, we do the same thing as we did for now our cylinder column. So one principle we did, no. So the same principle. What is usually done is this moment is converted into a eccentricity. Okay. So therefore, this based on this eccentricity, you will have your if it was just purely axial load, the pressure on bottom of your footing would have been same. It would have been a rectangle pressure distribution like this. Okay, if it was purely axial load. So when you have this kind of a load, you will have a different pressure distribution. Okay, which may look something like this. Okay. So corresponding to, so if it was only P, probably the pressure distribution would have been like this. This would have been the case if it was only purely axial. So when you have moment also acting, you see that on one side, the pressure increases beyond what it is there for P, and on the other side, it decreases beyond what would have been there for just P. Okay. So basically, because the moment is acting this side it will tend to press into the soil more. And on this side, it will be tending to pull the footing up. So therefore, the pressure decreases here, the pressure increases here. Okay. So this is if you have both of them. Okay. So there are three conditions that are used over here. One is, so I am not going into how this is arrived. I'm just telling you the final condition. So the case one is you can calculate your maximum and minimum pressures based on this formula. Okay. P plus delta P. Delta P is nothing but your back soil load. Okay, whatever load is coming because of this back soil. So that one. Okay, that is P. That's only delta P. P is whatever is coming from the column. So P plus delta P by A plus or minus P plus delta P into E divided by Z. Okay. So this is something that you can use where E equals the moment divided by, okay, or another is probably can just better thing, why to write like this. Let me just write M by Z. Any idea what is capital Z? What is capital Z over here? What is A? What is Z? What is A? What is Z?
So A is area.
area.
A is the area. Okay. Z?
Effective depth.
No, not effective depth. This is capital Z, not small z. It's basically your, you would have heard of this. It's okay, it's the section modulus of your footing cross section. Okay, it's the section modulus of your footing cross section, depending on the direction of your movement. Okay, so if it's this direction movement, you take this section modulus. Okay, and if it's the other direction section movement, you take the other section, the section modulus along that particular direction. Okay, so the case one, is for a case where, so this is a general formula. So case 1, I say if my E is lesser than or equal to L by 6, sorry, not L by D, L by 6. Okay, then I say this equation itself changes its form, it becomes Q max or minimum equals P plus delta P divided by A. Okay, and of course if I write M as E into P plus delta P, okay, then this becomes 1 plus or minus 6E by L. Okay, so you may be wondering where the 6 and this thing comes. So basically this section modulus, it can be just rewritten as Z equals BL square by 6. If you remember, or if it's a rectangular section, I is equal to BD cube by 12, Y minimum is D by 2, so therefore you will get Z is equal to BD square by 6, I by Y. So that's how you get BL square by 6, and then you just substitute that, you get 6E by L, because A is also B into L, no, because of that. Okay, so this is so this is when you get this kind of a pressure distribution. Okay, so if you have a case where this is the case that we always want. We want always E to be lesser than or equal to L by 6, in which case we will have all the soil pressures acting in the same direction. Okay, so basically all the pressure acts. Oh, I drew the mark around. So all the soil pressure will be acting in the same direction, or all of it acts as a pressure on the particular slab. Okay. However, if E becomes greater than or equal to L by 6, what will happen to the soil pressure is, your soil pressure becomes like this. Okay, you get soil pressure acting like this, which corresponds to a case where if you have your footing, this side of the footing till this particular point tends to be lifted up from the soil. So you have a case where the footing will tend to lift up on one side, which is not a good thing. So therefore, this is something that usually people tend to avoid when you dimension your footing. If you have moment plus axial load, you should fix your L by B dimensions such that you are able to avoid this condition. Okay, so it is only when E is lesser than L by 6, you have a case where your entire footing is being subject to the same downward pressure. Okay, so this is the thing that I wanted to talk. These are the basic concepts with regard to the design of footings. The remaining aspects we'll be seeing next week when we do a problem. Then and there I'll tell you what some of the provisions are. Okay, and one thing I forgot to mention is always this clear cover thing. Okay, clear cover for a footing. So compared to a normal beam or column, or compared to anything that is above the ground, okay, beams, columns, are the things. What do you think the clear cover should be for a footing? Can it be more lenient or should it be more strict?
It should be more, sir.
Why?
Like in soil there will be alkaline, so lower alkaline reaction.
Soil will have what?
Like soil will have more alkalinity.
Alkali.
Yes, sir. So to avoid
Alkalis, the salts may be there. Okay, and more than anything, there may be water it may be moist. Okay, so because of these reasons, you need should be greater than your beams, columns, and anything on the superstructure. The minimum that is specified for normal exposure conditions is 40 mm. You should not give lesser than 40 mm. Okay. In any case, so this is one thing that I forgot to mention. Anyway, so we'll stop with this and start working on your assignments. So start working